Welcome to Complex Analysis, Lesson 17. We're going to cover Cauchy's integral theorem, Cauchy's formula, and the generalization of Cauchy's formula, as well as several examples of each. On this slide, we're going to talk about the deformation invariance theorem. And it says that if you have two simple closed contours that can be deformed into each other, then the integral over those contours is the same. Here's this theorem more formally. If f is an analytic function in a domain D containing loops gamma sub 0, gamma sub 1, such that the loops can be continuously deformed into one another, then the two integrals equal to each other. I'm not going to prove it here. There's a proof in the book by Saff and Snider, which I've referenced several times. And I also found a set of lecture notes which are freely available. I'll put the link in the information for this lesson, and you might want to go there if you're interested in the proof. Okay, so let's look at a few examples of what we mean by continuous deformation between different contours. I have a few contours shown here on the right. So let's take an easy case first. So gamma sub 3, which is sort of a squiggly contour, can be continuously expanded out into a circle and then shrunk down into the size of this circle and then moved here. And so gamma sub 3 and gamma sub 2 are deformable into each other. We could also go from gamma sub 1 to gamma sub 2, but there's a little bit of a wrinkle here in addition to the size difference. What you do is to deform one into the other, you shrink gamma sub 1 into a point, and then you expand it out, but when you expand it out, you change the direction, and you also move it to the position of gamma sub 2, and in that way, gamma sub 1 and gamma sub 2 are deformable into each other. So the basic operations of continuous deformation is sort of like re-stretching or reforming the shapes. You could think of maybe a rubber band where you can form it into different shapes. And you can either contract or shrink, and then you can move. So you can move from one to the other, and then you can also reverse direction by shrinking down to a point and then expanding out again and reversing the direction in the process. Okay, there's a more formal definition, but hopefully this intuitive definition is sufficient. We're not going to be dealing with any particularly complex curves, so hopefully this kind of high-level definition of deformation is useful and helpful. Okay, we have another concept. It's called simply connected. I want to talk about that on this slide here, but first, maybe a few more examples of continuous deformation. So loop on the right, loop gamma sub 0 cannot be continuously deformed into gamma sub 1 without leaving the domain D. There's no way of going between these two because you have a hole here in your domain, and you can't, if you think of this as a rubber band and the hole is something you're not able to cross over, then there's no way of getting from gamma sub 1 to gamma sub 0. And the same problem between gamma sub 0 and gamma sub 2, and between gamma sub 1 and gamma sub 2. They're all not deformable into each other. What you can do is deform gamma sub 0 into gamma sub 4. You basically stretch it a little bit to make it more elliptical, and then you move it to gamma sub 4's position, and vice versa. So we have a few more examples of continuous or deformation, or at least in some cases examples where you're not able to do it. So the other concept I want to talk about here is something called simply connected domain. So it is a domain, it's open, and connect it. So you can go, for example, in this gray area here, you can pick any point and draw a line, curved line between the points. So you can go from, say, here to here without leaving the domain. But it's not simply connected because you're not able to compress or deform every loop into a single point. So we can see here we had these two problem areas, these two holes in our domain, and we had an example of a loop here, gamma sub 1, which we're not able to deform into a single point because of the hole here, and the same problem for gamma sub 2. So the reason I'm bringing this up is several of the theorems that follow assume that your function is defined in a simply connected domain that doesn't have holes in it. The holes typically are singularities in the function, and we'll see later that we need to draw our domain so that we avoid those holes, which, as I say, are excuse me, are typically singularities. Once we have the deformation theorem, Cauchy's integral theorem follows fairly directly. Let me state the theorem. If f is an analytic function in a simply connected domain, or maybe I should say within a simply connected domain D, and gamma is any loop, i.e. closed contour in D, then the integral about gamma of f of z dz equals 0. And the reason this follows from the deformation theorem is that in a simply connected domain, we can compress or shrink any loop into a single point, and we earlier defined the integral over a contour that's a single point to be 0. So this follows pretty directly. And the next theorem that we have here follows from some of our previous theorems, including the Cauchy integral theorem. So an analytic function, f, in a simply connected domain D has an antiderivative, has contour integrals that are independent of path, and all its loop integrals are equal to 0. So that the loop integrals of f, in terms of a proof I should say, that the loop integrals of f are all equal to 0 follows from our theorem here, because we have the conditions of this theorem in 128, also in 129, if f is analytic in a simply connected domain. So we get this first part of the theorem, but then the second two parts follow from the theorem 126 from the previous lecture, where we had an equivalence between three different facts. And one was if all the loop integrals are equal to 0 in a domain, then you have path independence, which is equivalent to path independence, and that's equivalent to the f having an antiderivative. As an example, consider the integral of the function f of z equals e to the z over z squared minus 16 over the contour of the modulus of z equals 2, which is a circle centered at 0 with radius 2. And the domain of interest will be the modulus of z less than 3. The reason we picked that is because when you factor the denominator, you see that the roots of the denominator are 4 and minus 4, and those are singularities where we know we don't have a derivative. In fact, the function's not continuous there, but the function is continuous and has a derivative within this domain of definition. And we can find the derivative using the quotient rule. It's the denominator squared, derivative at the top, which is e to the z, times the denominator, minus the numerator times the derivative of the denominator, which is 2z. And you factor out an e to the z, and you get z squared minus 2z minus 16 over z squared minus 16 squared. And so f is analytic in the simply connected domain modulus of z less than 3, and we have by the Cauchy integral theorem that the integral about this particular contour modulus of z equals 2 is equal to 0. So we didn't need to do any integral computation. We just needed to verify that the function of interest was continuous and had a derivative in the domain of definition, and the contour was within the domain of definition. Okay, we have another example. We want to find the integral of this function here, which I've factored out the denominator so we can see there's a singularity at z equals 1 and z equals 2. And we want to take the integral over this contour that I've drawn here. Really, the actual shape, as we'll see, doesn't matter. What's important is that we have two singularities here, so we need to somehow deal with those. And that's a little bit complicated. I'll show that in the next slide. But for the time being, let's just consider our contour of interest gamma, and we'll break that into two parts. So we'll have gamma sub 1 that goes from this point on the x-axis to this point on the x-axis, and then gamma sub 2 is the part of the contour that's below the x-axis. Continuing with our problem, we're going to replace gamma sub 1 and gamma sub 2 with simpler to evaluate contours. We'll start with gamma sub 2. I want to replace it with this dotted line contour, which is a straight line, a semicircle about 1, another straight line, a semicircle about 2, and another straight line. And the main point here is that this dotted line contour, gamma sub 3, has the same initial and terminal points as gamma sub 2. And if we draw a domain where f of z is analytic and continuous, so basically at any domain that excludes the two singularities but includes our two contours of interest, gamma sub 2 and gamma sub 3, then we know from a previous theorem that if f of z is continuous analytic within this contour here, this domain, then the integral over gamma sub 3 of f of z equals the integral of gamma sub 2 over of f of z. And so we can replace gamma sub 2 with gamma sub 3, which is what I've done here. Then you can do the same thing on the other side. Draw a domain where f of z is analytic and continuous on the boundary of the domain and within it. So within this blue domain, f of z is analytic and continuous, and gamma sub 1 and gamma sub 4 have the same initial and terminal point. Gamma sub 4 is just a straight line, a semicircle, straight line, semicircle, straight line. And so we're going to say that the integral of gamma sub 1 of f of z and the integral of gamma over gamma sub 4 of f of z are the same by previous theorem because of the function being analytic within our blue domain here. And so we will replace z sub 1 with gamma sub 4. And so we're left, we reduce the problem to evaluating these two integrals, but a couple advantages here. This line integral a and x are in different directions, so they cancel. B cancels with y, and the integral over c cancels with z. And we're left with a semicircle about 1, and the rest of it is another semicircle above 1. So we put those two together and we get a circle, contour circle about 1. We'll call that C sub 1. In a similar way, we get a contour circle about Z sub 2, and our problem reduces to just evaluating the f of z over these two circles, which we'll do in the next slide. Okay, so the two circles, I should say, that we had in the previous slide, this C sub 1 was about the point 1, singularity 1 of f of z, and then this C sub 2 was about the singularity at point 2. So what we do is we represent our function. This is our f of z. We've already factored it earlier, and then we try to write it in terms of partial fractions. If you remember, we had a technique from several lessons ago where we can find the value of a and b by taking limits. So if we take z minus 1 times the right here, then we get a, and then z minus 1 over z minus 2 times b. But when you plug in z equals 1, this drops out, so you just get a. And then when you multiply z minus 1 and take the limit of this times this term, this expression, then the z minus 1's cancel and you get 1 plugged into z, and you get 2 minus 5, which is minus 3 over minus 1, and you get 3. And you do the same thing to find b, and you get minus 1. So let's continue on the next slide. We're almost done. Okay, so let's finish our integral evaluation. We found the values for the partial fractions. So f of z over gamma equals the integral over c sub 1 plus the integral over c sub 2. We plugged in our values for the partial fractions here and here. And what I want to do is make use of a result from example 2 in previous lesson 15, where we had the integral about a circle centered at z sub 0 of this function 1 over z minus z sub 0 equals 2 pi I. So we're going to use this twice. You notice here this first term is of this form, and our 1 is inside of the circle. So that integral is 3 times 2 pi I. Then the second part is a 0. You get 0 because the singularity 2 is outside of the circle C1. So the integral of this is just 0. And then when you're using this again on the first part, actually 1 is outside of the circle centered about z equals 2. So this one's 0. But then the second part is of this form here because the 2 is the center of the circle C sub 2. And it's just minus 1 times 2 pi I, and you subtract 2 pi I from 6 in pi I, and you get 4 pi I. Okay, Cauchy's integral formula. Let's state that if a function f of z is analytic in a simply connected domain D containing the positively oriented simple closed contour, a loop, gamma, and w is any point inside of gamma, then f of w equals 1 over 2 pi I times the integral of f of z divided by z minus w. So notice the w here is the w here in the integral. And a proof, it can be found in Theorem 14 of section 4.5 of this book that I've referenced now several times, Saff and Snider, if you're interested in the proof. We can use Cauchy's integral formula to evaluate an integral, which we'll do on this slide. So our integral is shown here, e to the z plus z squared minus 2z over z minus I. And our contour is the circle centered at I plus 1 of radius 3. Notice that our singularity I is within this circle, and it's traversed once in the positive direction, counterclockwise, since we're talking about a circle. So f of z equals e to the z plus z squared minus 2z is analytic over the entire complex plane, so it's analytic on and inside of our circle, our contour. And if we apply Cauchy's integral formula, noting that I is inside of our contour, I mentioned that already, we have this here. Notice I took the 1 over 2 pi I and I multiplied it by both sides, so you get 2 pi I times f of I, notice the I here and here, is equal to just f. So we just need to evaluate f at I should say, and we just put that in there, so we get e to the I squared is minus 1, then minus 2I, and that's our solution. We can generalize Cauchy's integral formula for derivatives beyond just the first derivative, and that's what I'm showing here. If f is analytic on and inside a positively oriented simple closed contour, and w is any point inside of our contour, then we have the nth derivative of f evaluated at w equals this expression here. And notice that looks very similar to our Cauchy integral formula, which I have here in the upper right. The proof is just a matter of taking the derivative with respect to w, which you can bring inside of the integral, and in that case it's basically a partial derivative. Z is sort of constant, and if you keep taking the second, third, fourth derivative, so forth, you're going to get this n factorial and then the n plus 1 term down here. So the proof is pretty straightforward. It's just using the Cauchy integral formula. And well, this is basically stating in words what this is showing you here, that if f is analytic in a domain D, then all its derivatives exist and are analytic in D. If you recall way back when I first introduced analytic functions in a previous lecture, I stated this, but I said we'll be proving it later on. So here's our proof. If f is analytic, then all its derivatives n equals 1, 2, 3 up to infinity or also exist, and in some cases they may be 0. For example, if you have a polynomial of degree n, when you get to the n plus 1 derivative, then you're 0 with all further derivatives. But other things like e to the z and other such functions do have an infinite number of non-zero derivatives. Okay, let's do an example of using the generalized Cauchy integral formula. We'll take our function, our example, from the Cauchy integral formula that we had done previously. It'll be the same contour, which was a circle. It's centered at I plus 1 with radius 3. We'll slightly modify the function. If you remember from the previous example, we just had z minus I to the first power. Now we have it cubed. So we need to make use of the generalized Cauchy integral formula to evaluate this. Our f of z is as before. It's analytic over the entire complex plane, so it's analytic on and within our contour. Then we use the generalized Cauchy integral formula. We multiplied the 2 factorial over 2 pi I and brought it over to the other side. So we get our integral equals 2 pi I over 2 factorial, the second derivative of f at I. If you take two derivatives of f, you get e to the z plus 2, and this term, it cancels, it goes to 0. Then you plug in I and you get e to the I plus 2. And so our integral equals pi I times e to the I plus 2. And we'll finish this lesson with just a statement of a somewhat famous theorem related to this topic. It's called Morera's theorem. And it says, if f is continuous in a domain D, and the integral, the contour integral of f of z equals 0 for every closed contour gamma in D, then F is analytic, and D. And if you're interested in a proof, there's one in the Wikipedia article. Just search Wikipedia for Moreira's theorem.